Hi guys, how are you? So so in our last lecture we discussed about Shannon's entropy and the classical information theory. Today let us take a kind of a high level view of what qubits are. So if you are here learning quantum computing and if you have heard about quantum computing on the internet, you are probably familiar with this word qubit. I mean, even if you don't understand it, you must have heard it somewhere. So qubit is basically the unit of information for a quantum system. Generally, like for a classical system, if you have the you know you can have zeros and ones. Like it generally works in the binary system based on the flow of electricity through the circuit, I mean through the transistor. So in quantum computing, we do not call the unit for information as bits, we call it qubits. Now, why qubits, or what's the difference between a normal classical physical bit and a qubit? So let's take this example. you know so in quantum computers, we basically take quantum particles and examine the state of the quantum particle, and based on that, just like for example, if you have in a classical computer you have transistors, and we basically examine whether the current is flowing through the transistor, and that's basically one. We interpret it as one, and if the current is not flowing through the transistor, we interpret it as zero. Similarly, in quantum computers also we have the quantum particles. It can be photons, electrons, whatever. Okay, and each of these quantum particles have their associated states, and we examine the states of the quantum particle. So if you have a quantum particle whose wave function is defined, can be defined by something like uh, 0 or plus, and plus beta uh, and minus. Okay, so I mean, different textbooks use different notations. I've used plus and minus. In many textbooks you'll find the notation plus and minus, while in some other textbooks you'll find the notation 0 and 1. Generally, 0 and 1 is actually more natural because we are moving away from classical computers which were using 0 and 1. So let me just change it to 0 and 1, but it doesn't really matter, I mean, with what symbol you represent the state, it doesn't really matter. In fact, you know, you can even replace the 0 and 1 in the binary with some two other symbols, okay, and that should represent the same thing. So anyways, so how you represent the state, the only thing that I wanted to, the only point that I wanted to put across was that how you represent the state, or with what symbol you represent the state, it doesn't matter. Many textbooks use plus and minus, many textbooks use zeros and one, it's all same. Okay, so this is the state of the quantum, I mean the quantum particle. Now the question is how, now the question is, uh, what, like for example, as we discussed, that it can be in either state 0 or state 1 depending upon whether the current is flowing through the transistor or not. This is for the case of a classical computer. Now in the case of a quantum computer, it can be either in state 0. Okay, the final version of psi can be in state 0, or it can be in state 1 in terms of, when it's kind of measured, because when you measure the quantum particle, the wave function collapses. But interestingly, it can also be in a superposition of both 0 and 1. That is, the quantum particle can be both 0 and 1 at the same time. Okay, this property is what we call in quantum mechanics the principle of superposition. A particle can be in more than one states at the same time, and this is the power of quantum computer. It basically comes down to how the qubits are designed. So basically in qubit, you can, how much information you can encode, okay, is higher than, let's say, what a classical computer or a classical bit would encode, because for each quantum particle you can actually encode, because they have multitude of states. I mean, we have 0 1, we can even increase it to 0 1 and 2. Okay, and then imagine the state can be both in 0 1, the state can be both in 1 and 2, the state can be both in 0 and 2, and so on and so forth. I mean, yeah, there will be more combinations. So the amount of information a qubit can encode is much higher than the amount of information that the classical computers were to encode. But there's a catch. The catch is that when you measure the quantum particle, the state of the quantum particle, it will either give you a 0 or it will give you a 1. Okay, the superposition that I'm talking about between 0 and 1, that's something that you're not going to get as a final output. Okay, because when you measure it, the wave function collapses, and it can be either in state 1 or it can be state 0. Okay, so the final output, the in the so if you see in when the when the measurement is completed, you can either have 0 and 1, but in the intermediate steps you can have more than 0 and 1. You can have superposition of those states as well. Okay, now quantum mechanics, because so what it tells us about, so what happens is when we measure the state. Now in classical computers, when electricity flows through the transistor, it can be in 0 or it can be 1. It's based on the flow of electricity. Now but in case of quantum computers, when we are measuring the state, this is the wave function. What is the probability that a quantum particle will be found in state 0, and what is the probability that a quantum particle will be found in states 1? So here you see alpha and beta. These are kind of coefficients, and these and the important thing to discuss here is that uh, alpha and beta are both complex numbers. Okay, and the second thing that I wanted to let you know is that if you multiply alpha with the conjugate of alpha, because both are you know uh, complex numbers, then you're going to get you know alpha, what is it, squared, right? So if you have basic understanding of complex numbers, you know that why this is true. I mean, I just forgot to mark it as conjugate, so let me just do that. Yeah, just to represent that it's a conjugate variable. So, and the similar thing is also true for beta. Like if you multiply beta with the conjugate of beta, you're going to get a beta squared. Okay, so the probability of finding this quantum particle with this wave function in state 0 is basically alpha square. Okay, and the probability of finding the particle in state 1 is beta square. Okay, and I'm talking about probabilities here. You might be a little confused because these are complex numbers, but remember, when you multiply a complex number with its conjugate, the answer is always real, right? So that is the reason the final answer for both these will be real numbers, and therefore the probability will also be a real number. Okay, so yeah, this is what, and this is what's about what this is all about what a quantum or a qubit stands for. Okay, and another thing that I wanted to discuss is the representation of this qubits. So yeah, I mean, this is one way to represent it, but it's not a very formal way, because a a particle can have many more states. Okay, not just one or two states. So, and as I discussed earlier, that these states, what they represent, doesn't really matter much. I mean, you can use plus, minus, 0, 1, whatever, it doesn't matter. What's important is these coefficients. I mean, the probability amplitudes, the alpha and beta, because because that what determines how the, I mean, what would be the probability of getting to state 0 or what is the probability of getting to state 1. So a better way to represent it is basically in the form of a, oops, sorry, basically in the form of a matrix where you can have the, you know, uh, it would be basically a column matrix where you can actually have just the coefficients. Okay, and this is a much better and much more I mean it's a better way to represent it rather than this. Okay, because it will I mean it will kind of vectorize the calculation. One of the reasons why we represent it like this is because these quantum states actually are very synonymous to what we have as the physical vectors in yeah, so that's the reason why we represent it in the form of vectors, like in the form of a column. Okay, but more on that I will discuss about when I'll talk about the linear algebra in context of quantum mechanics. So in that section I'll talk about vector spaces, I'll talk about the Hilbert space and how how these quantum particles or the states of the quantum particles are synonymous to physical vectors. But for this lecture, this is enough information. Okay. So see you in the next lecture. Goodbye till then.